Good afternoon everyone. My name is Satish Lodam and I am working as an IT architect with IBM. I have 14 years of experience in the field of Oracle products and into infrastructure managed services. Today I am planning to kickstart a multi-part discussion on Oracle database architecture, and hence the name for this presentation is Exploring the Oracle Database Architecture. Many people in the Oracle DBA and development world struggle to understand the way the Oracle database works. It is due to the fact that the product is very complex internally but very user friendly otherwise. Many things are not documented due to the encapsulation that we want to hide unwanted details from the larger audience, and many other features are hard to find and locate. This would be my honest attempt to explain in simpler terms and with appropriate demos the architecture of the Oracle database. A famous British architect once said, "In pure architecture, the smallest detail should have a meaning or serve a purpose." So let's get started with part 1 of this series, Exploring the Oracle Database Architecture. In this session, I would talk about Oracle Database Server Software Components, Oracle Database Architecture Diagram, PGA and Database Instance Connection, SQL Statement Processing, SQL Statement Processing with an example, SQL Statement Parsing, the library cache memory component, library cache with respect to cursor sharing with appropriate examples, library cache and adaptive cursor sharing, which is a 11G new feature, data dictionary cache, which is also called as row cache, the server result cache, which is another component within your shared pool, miscellaneous memory allocations and control structures within shared pool, and memory allocations in shared pool. So let's get started with our first point, which is understanding the Oracle RDBMS server software components. So Oracle RDBMS server software, like any other application software, is a collection of programs, executables, libraries and documentation. A program in general is a dormant piece of executable code installed on your computer's hard drive. A program in itself is lifeless. It is of no use until we run it, until we execute it. When we execute it, we load the program, and by program I mean executable instructions belonging to that program and the data belonging to that program. We loaded it into the main memory of your computer, the random access memory, RAM. The CPU then fetches these instructions from RAM and starts acting on it. Some simple programs, when run, result into one process at runtime, whereas other complex programs would start many different processes at runtime. A process is a running version of a program. Oracle database is one such massively complex program which when executed spawns many runtime processes. Each process would consume some amount of memory and some amount of CPU. Each process is tasked with some activity which it is a specialist of. When we run Oracle, we essentially load the program, both the executable code and the program's data, into the main memory RAM of your computer. The running version of this program is called as an Oracle instance. Like any other running program, Oracle instance also requires main memory, and it also spawns many processes at runtime. Some of these processes are mandatory, while others are optional. By optional, we mean depending on the configuration, you may or you may not see these processes. Whereas the mandatory background processes are always there and are always required for your Oracle instance to run smoothly. If you kill any of these mandatory processes, your instance would terminate abruptly. Oracle instance also needs a large amount of RAM for its operations. The RAM allocated to the instance is divided into SGA, System Global Area, also known as Shared Global Area, and PGA, the Program Global Area, also known as the Private Global Area. As the name indicates, SGA is shared by all the connected user sessions to this database instance. How big or small the SGA would be is decided by the DBAs. Irrespective of the size of your SGA, it hosts many different memory allocations within it. Each of these memory allocations serve a purpose and supports execution of SQL statements in a tangible or an intangible way. Some of the major memory allocations within your SGA are shared pool, database buffer cache, redo log buffer, large pool, Java pool, and streams pool. Inside the shared pool, you have smaller, more memory allocations such as library cache, data dictionary cache, which is also known as row cache, the server result cache, the result pool, and miscellaneous other memory allocations for the control structures such as onQueues and latches. Inside the database buffer cache, you may have default pool, keep pool, recycle pool, and 0 or more non-standard database buffer caches. It depends upon the way you have configured it, depending upon your requirement. The other smaller parts of your instance's memory is PGA, which is privately held by the background processes and by the server processes run by your instance. So note, for your instance, there is only one SGA, but there would be many PGAs. The other part of your RDBMS server software is the Oracle database. By database, we mean the set of physical files where the user data in the tables, indexes, materialized views, index organized tables, etc. is stored. These files, apart from storing user data, also store system generated metadata. This metadata is often referred to as data about data. This is generated and maintained and managed and purged by Oracle depending upon the user's action. Some of these files store the user transactions as they occur, while some files store the history of all such transactions in the past. Some files are internally used by Oracle instance to store control information, without which your instance is helpless. There are many different types of files, but to list a few, we have in general data files, control files, redo log files, temporary files, parameter file, archived redo log files, password file, log and trace files, block change tracking files, and network configuration files. Now, with a lot of text on this slide, things are looking ugly and more confusing. So let's calm down and have a look at the diagram of whatever we just talked about. Oh, aha! This is much better than the audio commentary on your last slide. So hold your breath for the next slide for a more colorful deja vu. So here you have the Oracle RDBMS server as a software where you have two major components of it, the Oracle instance and the Oracle database. An Oracle instance has memory and background processes. The memory itself is given for SGA and for PGA, whereas the background processes could be classified as mandatory and optional. Within SGA, you have multiple other memory allocations such as the database buffer cache, the redo log buffer, the large pool, the Java pool, the streams pool. Let me zoom on to this area. Within shared pool, which is a component of your SGA, and this SGA in turn is a component of your memory, and this memory is part of your Oracle database instance. So within shared pool, you have library cache, row cache also known as data dictionary cache, the result cache of the server, and miscellaneous other memory allocations for various different control structures such as on queues and latches. The database buffer cache in turn could have default pool, keep pool, recycle pool, and other non-standard database buffer pools, database buffer caches. You have redo log buffer, you have large pool, you have Java pool, and you have streams pool. The other part of your Oracle instance, as I said, is background processes, some of them mandatory, such as DBWN, the database writer, the log writer, LGWR, the CKPT, the checkpoint process, the service monitor, SMON, the process monitor, PMON. Note, all of them are mandatory background processes, whereas the other background processes are optional. Depending upon your configuration, you may or may not see them, such as the archiver process, ARCN, the recoverer process, RECO, the dispatcher process, DNNN, where NNN are the numeric digits or the numbers. So you can have up to 999 processes. Then you have shared server processes marked as SNNN and MMON, which is the memory monitor. The other part of your RDBMS server software is the Oracle database, which is collection of files which you could see on your hard drive, the data files which stores the user data and systems metadata, the redo log files which stores the recently executed transaction records. You have control information in control file. It's absolutely a mandatory file for your Oracle instance. You have archived redo logs, which are historical records of your redo logs. Whereas redo logs records the recent transaction history, an archive log is a perpetual transaction history of whatever users would have run against your database. And then you have the parameter file, where you mention certain configurable parameters. Some of them are mentioned by DBAs, others could be mentioned by the developers. Although they may not have privilege to add those parameters on their own, they would often ask a DBA to add certain parameters depending upon their requirement. Now, this diagram is much better than the previous audio commentary, but the next slide is even better. So you are going to relive your experience, the deja vu. On to the next slide, which explains the Oracle Database 12c architecture diagram. So oh my God, this is how the Oracle 12c database architecture in its full blossom looks like. Have a look at it. I know. The only question on your mind is, who would read this whole diagram? Well, I would read it for you now. First, I would start with the background processes. Next, I would read the memory structures, the SG and the PGA. And last, I would look at files on the disk. So don't bother even if you keep missing a couple of details here and there. We are going to revisit each of them in a deep dive session that we are planning to do in this series. So let me get started off reading the background processes. This diagram, I have added hotspots. So the moment I take it to a particular point, there would be a screen tip. So I'm going to read these screen tips for you. Not that you have to remember all of them. But let's get started from VKRM. The virtual scheduler for resource manager, VKRM, manages the CPU scheduling for all managed Oracle processes. The process schedules managed processes in accordance with an active resource plan. RCBG, which is the result cache background process. This process is used for handling invalidation and other messages generated by server processes attached to the other instance in the Oracle real application cluster configuration. MMan, which is the memory manager. This process performs the resizing of memory components on the instance and serves as the instance memory manager, also sometimes called as the memory broker. This is especially used when you are using the automatic memory management feature in 11G or automatic shared memory management feature in 10G, which is basically called as dynamic memory or dynamic SGA. MMon, which is memory monitor or manageability monitor. MMon performs many tasks related to manageability, including taking automatic workload repository AWR snapshots and performing automatic database diagnostic monitor ADDM analysis. The MNNN performs manageability tasks dispatched to them by the MMON process. MMNL, which is the Manageability Monitor Lightweight process. The MMNL process performs many tasks relating to manageability, including active sessions history capture and metrics computation. PMON, the process monitor. PMON periodically performs cleanup of all the following processes that died abnormally: sessions that were killed, detached transactions that have exceeded their idle timeout period, detached network connections which have exceeded their idle timeout. In addition, PMON monitors, spawns and stops the following as needed: dispatcher and shared server processes, job queue processes, pooled server processes for database resident connection pooling, and restartable background processes. Another thing that PMON is responsible for is the dynamic service registration with the listener process. SMON, System or Service Monitor. SMON performs many database maintenance tasks, including creating and managing the temporary tablespace metadata, reclaim space used by orphan temporary segments, maintains the undo tablespace by making it offline, and shrinking the undo segments based on undo space usage statistics. It cleans up the data dictionary when it is in a transient and inconsistent state, maintains the system change number SCN to time mapping tables used to support Oracle Flashback features. In an Oracle Real Application Cluster environment, the SMON process of one instance can perform instance recovery for other instances that have failed. SMON is resilient to internal and external errors raised during background activities. RECO, the recovery process. RECO uses the information in the pending transaction table to finalize the status of in-doubt transactions. At timed intervals, the local RECO attempts to connect to the remote databases and automatically complete the commit or rollback of the local portion of any pending distributed transactions. All transactions automatically resolved by RECO are removed from the pending transactions table. The SGA allocator, SANN, which is the SG allocator, is a small fraction of SGA is allocated during the instance startup. The SG allocator process allocates the rest of SGA in small chunks. The process exits upon completion of the SG allocation. The possible processes are from SA00 to SAZZ. We have DBRM, Database Resource Manager. This process sets resource plans and performs other tasks related to the Database Resource Manager. If a resource plan is not enabled, then this process stays idle. EMNC, the EMON coordinator process. The EMNC coordinates event management and notification activity in the database, including streams event notification, continuous query notifications, and fast application notifications. GEN0, generic task execution, performs general tasks on behalf of other background processes, mainly to offload some potential blocking tasks. VKTM, the virtual keeper of time, VKTM acts as a time publisher for an Oracle instance. VKTM publishes two sets of time, a wall clock time using a seconds interval and a higher resolution time, which is not a wall clock time, for interval measurements. The VKTM timer service centralizes time tracking and offloads multiple timer calls from other clients. PSP0, the process spawner, spawns other Oracle background processes after initial instance startup. AQPC, which is Advanced Queue Process Coordinator, which is responsible for performing administrative tasks for AQ master class processes, including commands like starting, stopping, and other administrative activities. This process is automatically started on instance startup. QMNN, which is the Advanced Queue Master class, which is responsible for advanced queuing related activities. Each of this type of process represents a single class of work item, such as advanced queue notification, queue monitors, and cross-process communication. QNNN, which is again a process related to advanced queuing server class. Each server class process acts on behalf of an advanced queue master class process. This relationship is maintained until the master requires services of a particular service process. Once released, the server class processes are moved to a free server pool. CJQ0, which stands for the Job Queue Coordinator. CJQ0 is automatically started and stopped as needed by the Oracle scheduler. The initOra parameter called as Job Queue Processes specifies the maximum number of processes that can be created for the execution of jobs. The CJQ0 starts only as many job queue processes as are required by the number of jobs to run and available resources in the system. Job slave processes JNNN are created and awakened by the job coordinator when it is time for a job to be executed. Job slaves gather all the metadata required to run the job from the data dictionary. The slave process starts a database session as the owner of the job, execute triggers, and then execute the job. After the job is complete, the slave processes commit and then execute appropriate triggers and close the session. The slave can repeat this operation in case of additional jobs needs to be run. OFSD, the Oracle File Server daemon, serves file system requests submitted to an Oracle instance. This background process listens for new file system requests, both management like mounting, unmounting, and exporting of mounts, and I/O requests, and executes them using Oracle threads. The RM, which is a rat masking slave. This background process is used with data masking and real application testing. It extracts and masks bind values from workloads like SQL tuning sets and DB replay capture files. The RPNN, which is a capture processing worker. The RPNN are worker processes spawned by calling DBMS workload replay has a procedure called as process capture. Each worker process is assigned a set of workload capture files to process. Worker processes execute in parallel without needing to communicate with each other. After each process is finished its own processing, its assigned files, it exits and informs its parent process. The number of worker processes is controlled by the parallel_level parameter of the process captured in the DBMS workload replay package. By default, parallel level is null, which means that the number of processes is determined by CPU count. When you set the parallel level is equal to 1, no worker processes are spawned. Mark AU for resynchronization coordinator. Mark essentially tracks which extents require resynchronization for offline ASM disks. Remember, this background process would only be seen in case of ASM configurations, which is for automatic storage management. This process runs in the database instance and is started when the database instance first begins using the Oracle ASM instance. If required, Mark can also be started on demand when disks go offline in the Oracle ASM redundancy disk group. OCFN, which is ASM CF connection pool, which maintains a connection to the Oracle ASM instance for metadata operation. RBAL, which is for ASM rebalancing master. In an Oracle ASM instance, this process coordinates rebalancing activity for disk groups. In a database instance, it manages Oracle ASM disk groups. Rebalancing is done to balance the I/O workload on all the participating disks within an ASM disk group. ONNN, which is for ASM connection pool. This process maintains a connection to the Oracle ASM instance for metadata operations. ONNN is a slave process, or the ONN slave processes are spawned on demand. Next is parallel recovery process, PRNN, which serves as a slave process for the coordinator process performing parallel media recovery and carries out tasks assigned by the coordinator. The default number of these processes is based on the number of CPUs on your server. DIA0, which is the diagnostic process. It detects and resolves hangs and deadlock situations. You have DIAG, the diagnostic capture process. DIAG performs diagnostic dumps requested by other processes and dumps triggered by processes or instance termination. In the Oracle Real Application Cluster environment, DIAC performs global diagnostic dumps requested by remote instances. You have CTWR, the change tracking writer. It tracks change data blocks as part of Recovery Manager block change tracking feature. The purpose is to enable fast incremental backups of your database without having a need to scan all the blocks from the Oracle data files. CTWR maintains a ready list of blocks which could be referred to by their addresses during the next incremental backups, and only those blocks are then read by our man during the backup, fast incremental backup of a given data file or for the entire database. ARCN for the archiver process. ARCN process exists only when you configure the database in archive log mode and automatic archiving is enabled, in which case the ARCN automatically archives online redo log files. LGWR cannot reuse and overwrite an online redo log group until it has been archived. The database starts multiple archiver processes as needed to ensure that the archiving of filled online redo log groups does not fall behind. Possible processes include ARC0 to ARC9 and ARCA to ARCT. The log archive max processes initialization parameter specifies the number of ARCN processes that the database would start initially during the instance startup. These processes are spawned when your instance goes from mounted state to the open state. You have TT00 to ZZ, which is used by your redo transport slave. This process ships redo from current online and standby redo logs to the remote standby destinations configured for asynchronous transport. TNN can run as multiple processes ranging between 00 to ZZ. Remember, this is only required when you have a data guard feature configured for your database to maintain a disaster recovery site to protect from catastrophic failure of a given site. So you maintain a remote geographic database in a different geographic location which acts as a disaster recovery site. Next one is LGWR, the redo log writer. You could have LG00 to 99 slaves. On multiprocessor systems, LGWR creates slave processes to improve the performance of writing to the redo log files. LGWR slaves are not used when there is a sync standby destination. Each log writer slave is responsible for writing the redo from one or more redo log buffer strands, which speeds up the performance of each redo write requested. Moreover, LGWR slaves are created to support multiple outstanding redo writes, thus increasing the overall throughput of the redo write operation. You have ACMS, which is Atomic Control File to Memory Service. It coordinates consistent updates to a control file resource with its SGA counterpart on all instances in an Oracle Real Application Cluster environment. The ACMS process works with a coordinating caller to ensure that an operation is executed on every instance in Oracle rack despite failures. ACMS is the process in which a distributed operation is called. As a result, this process can exhibit a variety of behaviors. In general, ACMS is limited to small, non-blocking state changes for a limited set of cross-instance operations. CKPT, the checkpoint process. At specific times, CKPT starts a checkpoint request by messaging DBWN to begin writing dirty buffers. On completion of individual checkpoint requests, CKPT updates data file headers and control files to record most recent checkpoint details. CKPT also checks every 3 seconds to see whether the amount of memory exceeds the value of PGA aggregate limit initialization parameter, and if so, it takes one of these actions. The sessions using the most memory will have their calls aborted. Parallel queries will be treated as a unit. If the total PGA memory usage is still over the limit, then sessions using the most memory will be terminated. Sys processes and fatal background processes will not be subjected to any of these actions described. Then you have DBWN, where N itself could range from 0 to 9 and from A to J. A database writer. The primary responsibility of the database writer process is to write database blocks to disk. It also handles checkpoints, file open synchronization, and logging of block written records. In many cases, the blocks that the database writer process writes are scattered throughout the disk. Thus, the writes tends to be slower than the sequential writes performed by the log writer. The database writer process performs multi-block writes when possible to improve the efficiency. The number of blocks written in a multi-block write varies from one operating system to another. The DB_writer_processes initialization parameter specifies the number of database writer processes to be started. There can be 1 to 100 database writer processes. The names of the first 36 database writer processes are from DBW0 to DBW9, and from DBWA to DBWZ. The names of the 37th and onwards processes would be through BW36 to BW99. This is a recent change into Oracle 12c. The database selects an appropriate default setting for your number of DB writer processes to be started. It also can adjust a user specified settings based on the number of CPUs and the processor groups. BW36 to BW99 are slave processes, whereas DBW0 to DBW9 and DBWA to DBWZ are the master processes. You have FBDA, which is a flashback data archive. When a transaction that modifies a tracked table commits, FBDA stores the pre-image of the row in the archive. The FBDA maintains metadata on the current rows and tracks how much data has been archived. FBDA is also responsible for automatically managing the flashback data archive for space, organization such as partitioning table spaces, and retention. FBDA also keeps tracks of how far the archiving of tracked transactions has progressed. Next one is TMON. TMON is a transport monitor. TMON starts the TTNN processes and monitors a number of redo transport processes for hangs and for death or for abrupt terminations. RVWR, which is the recovery writer. RVWR writes flashback data from the flashback buffer in the SGA to the flashback logs. RVWR also creates flashback logs and performs some tasks for flashback log automatic management. Then you have LREG, which stands for Listener Registration Process. The listener registration process notifies the listener about instances, services, handlers, and endpoints. Then the very important server process. There could be many. An Oracle process that communicates with the client process and Oracle database to fulfill user requests. The server processes are associated with a database instance but are not part of the instance, means they are not part of the background process mechanism. Then you have the DNNN, which is the dispatcher process. In the shared server architecture, clients connect to a dispatcher process, which creates a virtual circuit for each connection. When the client sends data to the server, the dispatcher receives the data into the virtual circuit and places the active circuit on the common queue to be picked up by an idle shared server process. The shared server process then reads the data from the virtual circuit and performs the database work necessary to complete the request. When the shared server must send data to the client, the server writes the data back into the virtual circuit and the dispatcher sends the data to the client. After the shared server completes the client's request, the server releases the virtual circuit back to the dispatcher and is free to handle other clients. Several initialization parameters relate to shared servers. Some of them are dispatchers, shared underscore servers, max underscore shared underscore servers, local underscore listener, and remote underscore listener. The SNNN, the shared server process. In the shared server architecture, clients connect to the dispatcher process, which creates a virtual circuit to each connection. And the dispatcher in turn then talks with the shared server process. This server process here is part of the dedicated server configuration architecture, whereas the SNNN process is part of the shared server instance configuration. You can configure your Oracle instance to run a dedicated server process for every user client's connection, or you can share the fixed number of shared server processes if you configure your Oracle instance in a shared server environment. You have PNNN, which is a parallel query slave process. Parallel query has two components: a foreground process that acts as a query coordinator and a set of parallel slaves, which is a PNNN, are the background processes. These background processes are spawned or reused during the start of the parallel statement. They receive and carry out units of work sent to them by the query coordinator. The maximum number of parallel query slave processes is controlled by the initialization parameter parallel_max_servers. Slave processes are numbered from 0 to the highest value that you have specified as per parallel_max_servers. You can also use the $, if the query is $, query, then these background processes are numbered backward starting from PZ99. Then you have the connection broker process, NNN. In database resident connection pooling, clients connect to a connection broker process. When a connection pool becomes active, the connection broker hands off the connection to a compatible pooled server process. The pooled server process performs network communication directly on the client connection and the processes requests until the client releases the server. After being released, the connection is returned to the broker for monitoring, leaving the server free to handle other clients. You have the user process. The client process is responsible for managing private SQL areas. The allocation and deallocation of private SQL areas depends largely on the application, although the number of private SQL areas that a client process can allocate is limited by the initialization parameter called as open_cursors. And then we have processes on this side, various different processes. These are pertinent to real application cluster configuration rack. The first one is LMSN, which stands for the Global Cache Service. LMS N, where N itself could range from 0 to 9 and from A to Z, maintains a locked database for Global Cache Service, GCS, and buffer cache resources. This process receives, processes, and sends GCS requests, block transfers, and other GCS related messages. These processes are very rack specific and are part of cache fusion. Then you have LMON. The Global On-Queue Service Monitor, LMON, maintains instance membership within Oracle instance. The process detects instance transitions and performs reconfiguration of GES and GCS resources. You have ping. Ping is a interconnect latency measurement process. Every few seconds, the process is one instance sends message to the other instance. The message is received by ping on the target instance. The time for the round trip is measured and collected. This process is again Oracle real application environment specific. You have then LMHB, which stands for the Global Cache, the Global On-Queue Heartbeat Monitor. The Global Cache On-Queue Heartbeat Monitor. LMHB monitors LMON, LMD, and LMSN processes to ensure they are running normally without blocking or without spinning. This process again is rack specific. Then you have LMD 0 to Z, which is global on-queue service. LMDN, background process on-queue resources managed under the global on-queue service. In particular, they process incoming on-queue request messages and control access to global on-queues. They also perform distributed deadlock detection. There can be up to 36 of these processes ranging from LMD 0 to 9 and then from LMD A to LMD Z. Note that LMD already existed prior to 12C. The only change is LMD 1 to LMD Z are new. The LDD 0 to Z are the slave processes spawned on demand by LMDN processes. They are spawned to help the dedicated LMDN processes with various tasks when certain workloads start creating performance bottlenecks. These slave processes are transient as they are started on demand and then they can be shut down when no longer required. There are up to 36 of these slave processes ranging from LDD0 to LDDZ. Then you have LCK, which is for lock process, manages global on-queue requests and cross-instance broadcasts. The process handles all requests for resources other than data blocks. For example, LCK manages library and row cache requests. Possible processes are LCK0 and LCK1. Then you have IPC0. The IPC0 handles very high rates of incoming connect requests as well as completing reconfiguration to support basic messaging and RDMA primitives over several transports such as UDP, RDS, InfiniBand and RC. Again, this process is rack specific. You have RSMN, which is a remote slave monitor. This background process manages the creation of slave processes and the communication with their coordinators and peers. These background slave processes perform tasks on behalf of coordinating process running in another cluster instance. Again, this is a rack specific process. Then you have SMCO, which is a space manager coordinator. This background process coordinates the execution of various space management tasks, including proactive space allocation and space reclamation. SMCO dynamically spawns slave processes of the type WNNN to implement these tasks in parallel. So here I finished documenting all the background processes with respect to the 12C Oracle database. Now let's move on to the memory structures. The first one I'm talking about is the system or the shared global area SGA. The SGA is a group of shared memory structures that contain data and control information for one database instance at a time. Within SGA, one of the largest memory allocations is shared pool. The shared pool is a portion of the SGA that contains shared memory constructs such as shared SQL areas, library cache, result pool, row cache, the server result cache, and the other control structures such as on-queues and latches. Within shared pool, you have library cache, an area of memory in the shared pool. This cache includes the shared SQL areas, private SQL areas in case of shared server configuration, PL SQL procedure and packages and control structures such as locks and library cache handles. Within library cache, you have the shared SQL area, an area in the shared pool that contains the parse tree and the execution plan for a SQL statement. Only one shared SQL area exists for a given unique SQL statement. Now this is very interesting. Apart from the shared SQL area, you may have in your library cache something called as private SQL area. A private SQL area holds information about a parsed SQL statement and other session specific information for processing. When a server process executes SQL or a PL SQL code, the process uses the private SQL area to store bind variable values, query execution state information, and query execution work areas. Do not confuse a private SQL area, which is in UGA, User Global Area, which is the shared SQL area which stores execution plan in SGA. Multiple private SQL areas in the same or different sessions can point to a single execution plan within the SGA. This can be only seen when you are running a shared server configuration. Then you have active sessions history buffers. The active session history statistics are samples of sessions activity in the database. The database samples active sessions every second and stores them in a circular buffer in the shared pool memory region of SGA. Any session that is connected to the database and using CPU or is waiting for an event that does not belong to an idle wait class is considered as an active session. Then you have reserved pool. This is 5% of the reserved memory of your shared pool by default. The reserved pool is a memory area in the shared pool that Oracle database can use to allocate large contiguous chunks of memory. Allocation of memory from the shared pool is performed in chunks. Chunking allows larger objects over 5 kilobytes to be loaded into the cache without requiring a single contiguous area. In this way, the database reduces the possibility of running out of contiguous memory because of fragmentation. Infrequently, Java, PL SQL, or some SQL cursors may make allocations out of the shared pool that are larger than 5 kilobytes. To allow these allocations to occur most efficiently, the database segregates a small amount of the shared pool for the reserved pool. By default, this is given by the shared pool reserve size init_ora parameter, and the default value for this parameter is 5% of the total size of your shared pool. Maximum one can configure it to be 50% of the size of shared pool. You have the data dictionary cache, also called as the row cache, a memory area in the shared pool that holds data dictionary information. The data dictionary cache is also known as row cache because it holds data as rows instead of buffers, which holds the entire data block. So when we talk about buffers here, it's an exactly one Oracle block on disk, whereas when I talk about the data dictionary cache, it's a row at a time. Then you have on queues. Both on queues and latches are locking mechanisms used by Oracle. When activities cannot be performed in parallel and you need to serialize access to certain control structures, you use on-queues and you use latches. On-queues are shared memory structures, kind of locks, that serialize access to database resources. They can be associated with a session or a transaction. Control file transaction, data file transaction, instance recovery, media recovery, transaction recovery, job queue, updating the same record by multiple sessions, protecting the multiple updates happening to the same record at the same time, are some of the examples implemented by on-queues. On-queues are more sophisticated mechanism of locking as compared to latches. Latches are used as a low-level serialization control mechanism used to protect shared data structures in the SGA from simultaneous access. Some of the examples of latches are cache buffers, LRU chain, row cache objects, library cache pin, log file parallel write, and there are many different latches. Both latches and on-queues, as I mentioned, are locking mechanisms, but I also said on-queues are more sophisticated locking mechanisms than latches. Now assume two processes are trying to do the same activity at the same time. Latches would only allow one of the process to do it, whereas many others willing to do the same activity will go for a random milliseconds of a sleep, and then they wake up at a random time. One which wakes up first will be the one that would get the latch handle. Whereas in on-queue, it is purely on a FIFO basis. When multiple different processes are trying to do the same prohibited activity at the same time, only one of them is allowed to do activity and others are put in a queue, which is a FIFO data structure. On-queues that way are more sophisticated than latches. Then I'm not going to this particular part of it, which is the global resource directory. The global resource directory, I'm just going to quickly sum up the GRD, which is very rack specific. To ensure that each Oracle RAC database instance obtains the block that it requires to satisfy a query or a transaction, Oracle RAC instances use two services: the Global Cache Service GCS and the Global On-Queue Service GES. The GCS and GES maintain records of the statuses of each data file and each cached block using a register called as a Global Resource Directory GRD. The GRD contents are distributed across all the active instances, which effectively increases the size of SGA for an Oracle RAC instance. After one instance caches data, any other instance within the same cluster, database can acquire a block image from the other instance in the same database faster than by reading that particular block from the disk. Therefore, Cache Fusion moves current blocks between instances rather than reading the blocks from the disk. When a consistent block is needed or a changed block is required on the other instance, Cache Fusion transfers the block image directly between the affected instances. Oracle RAC uses the private interconnect for inter-instance communication and block transfers. The GES monitor and the instance on-queue processes manage access to Cache Fusion resources and on-queue recovery processing. So I have not touched base upon in greater details the various different memory structures within your shared pool, which are very rack specific. Then you have a flashback buffer. When flashback database feature is enabled, the background process recovery writer RVWR is started. This background process periodically copies modified blocks from the database buffer cache to the flashback buffer and sequentially writes flashback data from the flashback buffer to the flashback database logs, which are circularly reused. So the modified buffers are copied to flashback buffers, which is itself a circular buffer, and they are then dumped to the flashback logs by the background process called as RVWR. The flashback buffer area, when database smart flash cache feature is enabled, part of the database buffer cache can reside in the flash cache. This buffer cache extension is stored on flash disk devices. A maximum of 16 files are supported. So assume that you have insufficient RAM. More the RAM, more the number of Oracle data blocks you can retain in memory. But given the restriction on RAM or the amount of physical RAM that you have installed on your machine, you might want to use the SSDs, the solid state storage devices, as an extension to your database buffer cache. In that, you would need flash buffer area, which is an extension to your database buffer cache. The database can improve performance by caching buffers in flash memory instead of reading from magnetic disk. You must configure a flash cache on either all or none of the instances in your Oracle Real Application Cluster environment. This flashback, the feature called as the database smart flash cache is only available on Oracle Solaris operating system and on Oracle Enterprise Linux. It's not supported on any other operating system. Then you have various buffer pools. A buffer pool is a collection of buffers. A database buffer cache is divided into one or more buffer pools, namely the default pool. This pool is the location where disk blocks are normally cached. Unless you manually configure separate pools, the only pool you would have in your database buffer cache is the default pool. Apart from default pool, one might want to configure keep and recycle pools. Keep pool is intended for blocks that were accessed frequently but which aged out of the default pool because of lack of space using LRU algorithm. The goal of the keep buffer pool is to retain the data blocks in memory, avoiding unnecessary I/O operations to fetch them back from the disk once they are aged out. Recycle pool. This pool is intended for blocks that are used infrequently. A recycle pool prevents objects from consuming unnecessary space in the default pool. Apart from the buffer pools, which are made up of blocks of standard Oracle block size, you may have table spaces with non-standard Oracle blocks. For such non-standard Oracle block sizes, you have to configure non-standard default buffer pools. The non-standard default buffer pools a database has a standard block size of 8K when not specified. You can create a table space with a block size that differs from the standard Oracle block. Assuming that I have selected an 8 KB of a standard Oracle block size, then you may have a probability that you might create table spaces where the block size is of 2K, 4K, 16K and 32K. For each of those non-standard block sizes, one has to reserve the memory in the database buffer cache using the initialization parameter db underscore nk underscore cache underscore size, where n itself in my case could range from 2 to 4 to 16 to 32K. Remember, 8K is not applicable because for standard blocks these memory regions are used. Then you have the redo-log buffer. The redo-log buffer is a circular buffer in the SGA that stores redo entries describing changes made to the database. Redo entries contain the information necessary to reconstruct or redo changes made to the database by a DML or a DDL operation. Database recovery applies redo entries to data files to reconstruct the lost user transaction. Then you have the large pool. The large pool is an optional memory area intended for memory allocations that are larger than is appropriate for shared pool. The large pool is different from the reserved space in the shared pool, which uses the same LRU list as other memory allocated from the shared pool. The large pool does not have an LRU list. Pieces of memories are allocated and cannot be freed until they are done being used. As part of the memory residents in the large pool, you have response queues. When the server completes the request, it places the response on the calling dispatcher's response queue. Each dispatcher has its own response queue. The dispatcher returns the completed request to the appropriate client processes. Then you have request queue. A dispatcher places a request on the request queue where it is picked up by the next available shared server process. A request from a user is a single API call that is part of the user SQL statement. The shared server process checks the common request queue for the new request, picking up a new request on first in, first out basis. You have the user global area. Much on this when I talk about PGA. The user global area is located in large pool only if you are running a shared server configuration for your instance. For a dedicated configuration, the UGA is part of the program global area. Then you have PX message pool. These are message buffers used in the parallel execution of statements. Then you have shared IO pool. The shared IO pool is used for large IO operations on secure file LOBs. This pool can be sized using undocumented initialization parameters. In any case, if it is too small, the database uses PGA memory. Then you have streams pool. The streams pool stores buffered queue messages and provides memory for Oracle streams capture process and apply processes. The streams pool is used extensively by Oracle Streams, which is now a deprecated product in Oracle 12c. Earlier was used for database replication. Unless you specifically configure it, the size of the streams pool starts at 0. The pool size grows dynamically as required by the Oracle Streams. Then you have the Java pool. The Java pool is an area of memory that stores all session-specific Java code and data within the Java virtual machine. This memory includes Java objects that are migrated to the Java session space at end of call. You have fixed SGA. The fixed SGA is an internal housekeeping area. The fixed SGA contains general information about the state of the database and the instance, which the background processes need to check, and information communicated between processes, such as information about locks. The size of the fixed SGA is set by Oracle database and cannot be altered manually. The fixed SGA size can change from release to release. So here I've described the SGA, the system global area. Now let's move on over to program global area. The program global area is memory specific to operating processes or thread that is not shared by other processes or threads on the system. Because the PGA is process specific, it is never allocated in the SGA. Some of the primary residents of PGA are SQL work areas. A work area is a private allocation of PGA memory used for memory intensive operations. As an example, a sort operator uses the sort area to sort a set of rows. Similarly, a hash join operator uses a hash area to build a hash table from its left input, whereas a bitmap area, merge area, uses the bitmap the bitmap merge operation uses the bitmap merge area to merge data retrieved from scans of multiple bitmap indexes. Then you have this UGA, which I earlier mentioned is part of your large pool if you are using a shared server configuration. In case of a dedicated configuration, the user global area, which comprises of session variables and Olap pools, is part of the PGA. And private SQL areas which in a dedicated server configuration are again part of the PGA, are otherwise in a shared server configuration are located in the shared pool. The user global area UGA is a session memory, which is a memory allocated for session variables such as logon information and other information required by database session. Essentially, the UGA stores the session state. The UGA must be available to a database session for the life of the session. For this reason, the UGA cannot be stored in PGA when using a shared server connection, because the PGA is specific to a single process. Therefore, the UGA is stored in the SGA inside large pool when using the shared server connections, enabling any shared server process access to it. When using a dedicated server connection, the UGA is stored in the PGA. Inside UGA, you have session variables, session variables. For example, if a session loads a PL/SQL package into memory, then the UGA contains the package state, which is the set of values stored in all the package variables at a specific time. Then you have Olap pool. The Olap page pool is also stored in the UGA. This pool manages Olap data pages, which are equivalent to data blocks. The page pool is allocated at the start of an Olap session and released at the end of the session. An Olap session opens automatically whenever a user queries a dimensional object such as a cube. Then as part of the private SQL area, you have persistent area. The persistent area contains bind variable values. A bind variable value is supplied to a SQL statement at runtime. When the statement is executed, the persistent area is freed only when the cursor is closed. While we were talking about this, I just noticed that we also have a description of a cursor here. A cursor in general is a current set of records. That's why the name cursor. A cursor is a name or a handle to a specific private SQL area. You can think of a cursor as a pointer on the client side as a state on the server side. Because cursors are closely associated with private SQL areas, the name cursor and the private SQL area is used interchangeably by various different authors. Now that we have finished talking about the memory structures, let's move on to files on disk. The flashback logs. Flashback logs are Oracle generated logs used to perform flashback database operations. The database can only write flashback log to the fast recovery area. Flashback logs are written sequentially and are not archived. They cannot be backed up to disk. Then you have the database and temp files. A data file is a physical file on disk that was created by Oracle database and contains permanent data for a database. This data could either be user data or metadata. The data file can be located either in an operating system file system or it can be put on top of a Oracle ASM disk group. A temp file is a temporary space on disk, part of temporary table space, which cannot contain permanent database objects like tables, indexes, materialized views, etc. These files are specifically used to create sort segments. When you intend to do a sort operation on a voluminous data and that the sort operation cannot be entirely done in the SQL work areas, especially in the sort area, then the entire data is divided into batches and the batches are sorted then in the SQL work area memory space of your PGA, and once sorted the temporary results are then written to the temp files. This keeps on happening in a recursive manner until all the data is sorted. So temporary files are used to store sort segments for a sort operation that spills out of the sort area memory region from your SQL work areas part of your PG. Then you have control files. It's a binary file that records the physical structure of a database and contains the names and location of redo log files, the timestamp of the database creation, the current log sequence number, the checkpoint information, the location of your data files, so on and so forth. It also contains the metadata of your RMAN configuration and RMAN backup metadata. Then you have the change tracking file, which is again a binary file used by RMAN to record the changed blocks to improve the incremental backup performance. They do not store the actual data blocks, but it stores the DBA, the data block address, since the last time the block was changed. The moment the block gets changed, the address of that block would be written by the CTWR background process into the change tracking file. Next time, when RMAN tries to do the backup of your database, instead of reading all the data files from start to end, it directly jumps to the change tracking file, reads the addresses of the blocks which got modified since the last backup, then directly reads those blocks from the data files and puts it in the image copies, not in the image copies, in the backup sets. You have the server parameter file. It is a server-side binary file containing initialization parameters, settings that is read and written to by the database. So how much you want to keep these memory areas. For each one of these, you have some parameter. All these parameters where the default value does not applies to you, all such parameters should be added into the server parameter file. Then you have the redo log files. The online redo log files is a set of 2 or more files that record all changes made to the database by users' transactions. Whenever a change is made to the database, Oracle generates a redo record in the redo log buffer. The LGWR background process writes the contents of the redo log buffer into the online redo log files on disk. The current online redo log is the one that is being written to by the LGWR process. When the LGWR gets to the end of the file, it performs a log switch operation and begins writing to the new log file. If you run your database in archive log mode, then each filled online redo log file must be copied to one or more archive destinations before LGWR can overwrite them again. The Oracle online redo log consists of 2 or more online redo log groups. Each group contains one or more identical online redo log members. Then you have the archived redo log, which is nothing but a content copy done by the archiver process from the filled redo log files. So once when the redo log file is full, the contents are copied by the archiver process and they are stored in the form of archived redo log in the archive destination. Archived redo log files is a copy of a filled member of an online redo log group made when the database is in archive log mode. After the LGWR process fills each online redo log with the redo records, the archiver process copies the log to one or more redo log archiving destinations. This copy is the archived redo log. RMAN does not distinguish between an original archived redo log and an image copy of an archived redo log. Both are considered image copies. Then you have the automatic diagnostic repository, ADR. Let me zoom into this one. The ADR is a system managed repository for storing and organizing database trace files and other diagnostics data. ADR provides a comprehensive view of all the serious errors encountered by the database and maintains all relevant data needed for problem diagnostic and their eventual resolution. The repository contains data describing incidents, traces, dumps, alert messages, data repair records, data integrity check records, SQL trace information, core dumps, and so on. The initialization parameter diagnostic_dest specifies the location for the ADR base, which is in the directory that contains one or more ADR homes. Each ADR home is used by a product or a product instance to store diagnostic data in a well-defined subdirectory structures. For example, diagnostic data for an Oracle database instance is stored in its ADR home, which includes an alert subdirectory for alert messages, a trace subdirectory for trace files, and so on. The easiest way to locate the trace files and the alert log is to run a select statement against v$diag_info dynamic performance view. Apart from this, you have MML or OSB. MML or OSB tape backup to or Amazon S3 cloud backup. The Oracle Media Management Layer MML API lets third-party vendors build a media manager software that works with RMAN. RMAN is a Oracle provided utility named Recovery Manager which facilitates backup, restore, recovery, cloning, standby database creation and reporting of Oracle databases. A media manager handles loading, unloading, and labeling of sequential media such as tapes. You must install Media Manager software to use RMAN with sequential media devices. Oracle Secure Backup OSB is an Oracle Media Manager that supplies reliable data protection through file system backups to tapes. The Oracle Secure Backup SBT interface also enables you to use RMAN to backup Oracle databases. All major tape drives and tape libraries in SAN, Gigabit Ethernet, and SCSI environments are supported. The OSB Cloud module is part of the OSB product family and provides the flexibility to take backup of your database to Amazon S3 cloud. Then you have the RMAN process. This is a server process running RMAN, which is Recovery Manager tool from Oracle. RMAN helps in backup, restore, recovery, reporting of your Oracle